the building of Sallingsund Bridge. Here we see listed the various parties connected with the building of the bridge. Firstly, the client, the road directorate, then the advisory group, and finally the 4 members of the Sallingsund consortium who designed and constructed the bridge. Here, in the north of Denmark, where the hills slope down to Sallingsund, we have built a connection between Salling and Mors. A bridge that not only benefits local traffic, but also supplies the missing link in the diagonal cross-country road through Jutland, from Aarhus northwest to Viborg, and Skive, and on across Mors to Tisted, right up to Hanstholm. Previously, the ferries plied between Pinen and Plagen, that is, the pain and the plague, 135 times a day. But finally the pressure of traffic was so great that there were often long waiting times. In addition to Sallingsund Bridge, adjoining roads and bridge structures had to be built, covering a total length of about 40 kilometers. The neighbouring roads pass through some of the prettiest scenery in Denmark. This is how it looked before the bridge. The connection was to lead through the hills called Legin Bjerge. On October the 5th, 1973, Per Milner, the head of the road directorate, signed the contract with the Sallingsund consortium, which consisted of the Danish engineering firms of Kampmann, Kierulf and Saxild and Højgaard Schultz, together with the French firm of Campion Bernard and the German firm of Polensky and Zöllner. At the international tender, these firms were the cheapest, offering an alternative project both for the substructure of the bridge and for the superstructure, based on prefabrication. On November the 19th, 1973, work was officially set in motion by the Minister of Transport. The head of the road directorate spoke first.
Dette sted, der meget snart bliver en aktiv byggeplads. Jeg vil gerne byde en særlig velkommen til trafikministeren. Vi er glade for, at ministeren har fundet anledning til i den travle periode at komme herop og sætte arbejdet i gang. Herr minister, mine damer og herrer, også jeg vil som repræsentant for Morsø Kommune gerne have lov til at byde jer alle hjertelig velkommen i dag, hvor arbejdet med Sallingsundbroen påbegyndes.
Then came the Minister of Transport.
Jeg tænker ikke på den nærværende valgsituation, men jeg tænker på navnene på skibene hernede. Jeg tænker på den ventetid, som de symboliserer, og jeg tænker også på den ventetid, som projektet her jo har været udsat for.
The bridge is 1,730 meters long, with normal spans of 93 meters, side spans of 51 meters, and 2 navigable passages of 60 by 26 metres. The 16-metre broad cross-section between the 2 windshields is divided into an 8-metre carriageway with cycle paths and pavements on both sides. Pier 1 is founded directly on the seabed. Pier 2 is founded on reinforced concrete piles. Most of the piers in the water are founded on steel piles, filled with concrete. Here is a model of the substructure for a pier in the water. It consists of tubular steel piles, piling template, pier box, and icebreaker. The complete substructure project was carried out from the site on Morse. Here are the stockyard and the production area for the tubular steel piles. The reinforcement for a piling template was prefabricated complete in one unit, before being transported to the casting platform. Here we can see the holes for the piles in the template's ring-shaped casing. A floating crane transports the template and lowers it down onto a special platform. Here, the reinforcement is bent for the pier box. The final length is measured and the rings are butt welded. Construction of the reinforcement for the lowest part of the pier box is in full swing. Shuttering for the lowest part of the pier box has now been erected on a piling template placed on a platform, and concreting is underway. The projecting steel bars are starter bars for the central part of the pier box. As the lifting capacity and the height under the hook of the floating crane are limited, the pier boxes are cast in the working dock in 3 stages, 1 stage for each platform, and at 3 different depths of water, so that the final casting takes place on the deepest platform. On the bridge centre line, there's about 15 metres depth of water, 15 metres of silt, 10 metres of loosely deposited shale, and under that the bearing layer of meltwater deposit. So we've got to get down below the level minus 40 metres to find a foundation layer, and it's this that has determined the choice of pile founding. In all, 3 bearing piles are driven for the piling template. They're provided with caps on which the template rests. Before these caps are constructed, the tops of the bearing piles are measured up in detail. The caps for the bearing piles are then tailor-made on land, using the measurements taken by the diver. The pile caps are fixed to the bearing piles with the help of a diver. The template is fitted with an alignment tower with optical plumb, so that it's possible from above the waterline to determine the position of the template. The template is temporarily provided with 3 bearing girders resting on the bearing piles. The sighting plate for the optical plumb is fitted. The template with its alignment tower is now ready for submersion. The correct positioning of the template is ensured from the shore.
Kjeld til gearet, kom.
Ja, det er gearet, kom ind, skifter.
Ja, hvordan er det med hældningen? Kom.
Hældningen er OK, skifter.
Ja, så er rammelæren sat.
And the positioning is controlled in the water with the help of the divers. A further check is made from both shores using the intersection of lines of sight. Here you can see the template with the holes through which the piles will be driven. The steel tubes for the piles have a diameter of 70 centimeters and an average length of 25 to 30 meters. The piles are driven through a guide tube which is kept in place from below by the template and from above by a girder system constructed between the wooden trestles and the pile driving barge. The lower 2 meters of the piles are filled with concrete and the piles are driven internally with the aid of a dolly. In the first instance, only a limited number of piles are driven. These are the test piles, together with a central pile and counter-action piles for the test loading. Test loads are carried out at all the piers. These results, together with the results of the previous geotechnical tests, determine the number of piles, the pile toe levels, and the positioning in the template. Now the counter-action piles and the test load pile can be cut to level, and the final pile driving can take place. For the first piles, a 12-ton monkey was used. Because of the difficulty of the pile driving, this was later exchanged for a diesel hammer with a 5.5-ton piston. The piles are placed in 2 conical surfaces, one with its intersection on the waterline, the other with its intersection in the bridge girder. Here we can see the template with the piles driven and shortened. Now comes the casting with underwater concrete around the pile heads. For this, mobile casting equipment is used, and the casting is made right up to the edge of the casing. To prevent corrosion, the uppermost part of the piles is reinforced with a prefabricated cage. Now the bearing girders for the template can be removed. Here is the casing, fully cast. The position of the concreted template is checked with the aid of the alignment tower. The pier box is equipped with a temporary cover. Air is pumped into the pier box so that a balance is achieved between its weight and the crane's lifting capacity of 200 tons. The pier box is transported out and lowered onto the template. The pier box is equipped with an alignment tower. If the template is out of line with the correct position, it's possible to position the pier box eccentrically in relation to the template. The joint between the template and the pier box is sealed with a rubber gasket. Then the icebreaker unit can be placed. It's transported out with the aid of a floating crane and placed on the top of the pier box. The space between the pier box and the icebreaker is filled with underwater concrete. A cover is fitted over the test load pile. The water is pumped out of the assembled units and a working chamber with normal pressure has been created. The pile reinforcement is raised up into place and the piles are cast. The ring-shaped body above the pile caps is reinforced and cast. In the same way, the icebreaker box is reinforced and cast too. The round tower in Copenhagen gives some idea of the size of the foundations. Here we see again the model of the completed substructure without pier shafts. The pier shafts are of reinforced concrete, cast in situ in shutter sections of roughly 3.5 meters each. As we can see, the bridge superstructure is made up of segments, standard segments in the spans and pier segments above the piers. All the girder segments are constructed at a field factory on the Salling shore. Here the reinforcement is assembled in units. These are the casting molds. A completed reinforcement unit arrives at the casting mold. Here in diagram form is the casting of standard segments. The principle is that the two segments that are to lie side by side in the bridge girder should also be cast against one another, side by side. The segments are placed in the storage yard. Here is a model of the bridge under erection. The launching gantry has just completed the erection of a T, consisting of two pier segments, 2 by 12 standard segments, and a closing segment. The heaviest segment weighs 128 tons. The gantry has a central support, a rear support, a front support and a mobile support. In the situation shown here, neither the front support nor the mobile support are in use. The gantry is equipped with cables which ensure distribution of the load between the central support and the end supports. A trolley is suspended under the gantry girder. Here, the gantry is being moved forward to begin the erection of the next span. In reality, the movement is much slower than shown here. The same goes for all the other model recordings. Now the gantry is in place. The front support is adjusted, and the gantry's cables are tightened to relieve the load on the central support, which is resting way out on the newly assembled cantilever section. The first pier segment, which is transported by low loader, is suspended from the gantry's trolley. A pier segment is removed from the storage yard by a portal crane and placed on a low loader. The segment is turned 90 degrees and the trolley with the segment is driven forward to a position in front of the front support. The segment is again turned 90 degrees and lowered into place. The top of the pier shaft is fitted with temporary bearings and adjustment devices. The second pier segment is similarly erected, together with the first standard segment on the Salling side. These are glued together and held by dividag rods, which are fitted inside in ducts embedded in the concrete, but shown here on the outside. The mobile support arrives on the low loader and is suspended from the trolley. The trolley is driven to the central support. The load on the central support is transferred to its auxiliary support by means of jacks. The central support's crossbeam is transferred from the main support to the mobile support. The trolley with the mobile support is driven to the pier shaft with the newly erected segments. The mobile support has taken over the role of the front support. Pressure is relieved on the central support and the gantry moves relative to the mobile support with the aid of the trolley's motor. When the gantry has moved out a certain distance, its cables are slackened. The gantry moves on until the central support is abreast of the mobile support. The gantry load is transferred from the mobile support to the central support. And the mobile support is carried by the trolley to the rear end of the gantry, where it's loaded onto the low loader and driven off. The gantry is now in the erection position. Continuing the erection using the cantilevered construction principle, segments are placed alternately on the moor side and the salling side. The segments are glued together and kept in place in the upper side by both temporary duvidag rods and permanent fasciné cables. A segment arrives on the loader and is suspended from the trolley. The trolley with the segment is driven forward to the lowering position. The segment is turned 90 degrees and lowered. During the passage of the end of the already erected girder, epoxy glue is applied to the joint surface of the segment and the upper part of the girder end. When all the 12 segments have been assembled on both sides of the pier shaft, the closing segment in the last span is lowered into place and is borne temporarily by a special girder construction. The segment is bolted to the previous one The final joint is sealed by in situ casting. In addition to the cantilever cables, which we've seen being tightened during the assembly of the span, there are cables in the lower section symmetrically positioned around the middle of the span, the so-called continuity cables. Here we see them being tightened. All that remains is to cast the edge beams and complete the bridge deck with road surfacing and so on. On May the 30th, 1978, Her Majesty Queen Margrethe II opened Sallingsund Bridge.
Og for alle i Danmark, for vores mange udenlandske gæster, overklipper jeg nu båndet og indviger hermed Sallingsundbroen.
The bridge is finished. for the benefit of the enterprising people in the district, for the good of the country's economic life, and for the pleasure of many tourists. Traffic flows easily and unhindered high over the Sound. Unhindered in spite of the ice that would otherwise have closed the Sound to the small ferries. An impressive new highway bridge in the Danish countryside.